Okay, dear friends, once again we have an interesting topic ahead of us. We are going to talk about analysis of variance this lecture. There are many ways of approaching this, and we'll get into that soon. However, I'll start by taking one step back and trying again to have an overview of where we are at in the course at the moment. I really like the fact that many of you have asked questions and given advice and suggested things and so on in our Moodle. That is truly wonderful. I like it a lot, and it helps us all, I think, in many ways. It is especially essential, I think, that we are working in this way when we are talking about statistical methods. Quantitative analysis has a reputation of being difficult. I don't actually believe that it is that difficult for anybody. But my mobile phone is giving me advice. It is, I think, overrated, hyped. The essence of statistical methods is just answering questions in a way that is concise and understandable, so that we actually get an answer that people get convinced by, so that there is a way of convincing people who think otherwise than we already do. But also the other way around. So it oftentimes we find that something that we hold dear, that we thought was one way, actually isn't, and that's also seriously important, maybe even more important. Many people have spoken about statistics. There are a lot of statistical jokes. I appreciate all of them. George Bernard Shaw once said that you have to be very intelligent to be moved by statistics. I think he intended it as a joke, but I take it very seriously. Not in the sense that the statistics themselves would move us. Not in the sense that you have to be very intelligent for it. I think what should move us is that we have something essential. Our message is something essential, that we are doing research on something that is truly worthwhile. We are providing an answer that should make people stop, should make people think, and we are providing it in a way that actually clarifies the situation and doesn't make it more confusing. And that kind of a serious message on an important issue should move any person, not just the intelligent ones. Okay. Once again, and you will see this once again later on, but just to remind you, we have these different types of scales, and from them we have different types of measures of the average and the variance within the scale, on the scale, perhaps you should say, I don't know. Anyway, so the typical situation that we are interested in here would be comparing means from different groups. So we would have one categorical or more categorical variables as independent variables, looking at the different groups in the independent variable, and then comparing their means to say, for instance, is there a difference between those who have had a treatment or not had a treatment, those who are male or female? Any kind of comparison between means is what we are out after today. And sorry, again, this has some Finnish here, but okay. In this, our situation here is simply that I just explained we have one or more categorical variable and one interval scale variable, and then if they work nicely, we can do an analysis of variance, ANOVA, among friends. And if the distributions are non-normal, if there are other problems, then typically we go for a non-parametric version of ANOVA. There are several, but we'll get there soon. So you can compare groups even if they are not, they don't fulfill all the criteria of an analysis of variance. But of course, the analysis of variance is the strongest way of doing it. So if the criteria are fulfilled, then that's where we are heading. So that's number one. And then if things don't go correctly, then some other version, some non-parametric version is okay too. I have tried to find you some videos again here on how to do an ANOVA. People who explain things more concretely or more directly or more quickly than I do, and I hope that you will find some of them useful for yourself. All right, getting to the real stuff here. So, as I said, the idea is simple. We have two or more groups, and we want to compare the means in these groups. And of course, to be able to count the means, then you have to have a interval scale variable there. There are some other essential requirements for analysis of variance as well. But first, we'll look at the terms that we will use here. So we have a dependent variable, which gives us the means. We are interested in comparing something, the kind of the outcome, for instance, of an experiment. People either know their math or don't know their math, and this kind of comparison. We also have independent variables, so the ones that we are trying to see if they have an effect on the dependent variable. In SPSS, we typically call them, or the program calls them, fixed factors, which is a little bit confusing since we use the factor analysis term factor there. Here we are talking about things like in factor analysis, we are talking about concepts that are not directly measurable, easily measurable. So we have to, instead of measuring intelligence, we measure different variables that we think express intelligence, and then from that we can have a factor analysis to see what that intelligence would then look like, the latent variable, hidden variable, or the hidden factor would kind of come out through this practical, through the items that we have used to measure it. Well, in this sense, we also have here factors, things that influence something else. So the fixed factor is simply something that is going to influence the dependent variable. And it should be, of course, a categorical variable, because then you have the categories are groups, and you can see if the groups have different means. Then we have a very old-fashioned but neat way of looking at ANOVAs. We have a one-way and a two-way ANOVA. Typically, a one-way ANOVA is an ANOVA with one independent variable, and we also have ANOVAs with two-way ANOVAs with two or more independent variables. I really don't think that these are that important. They are simply used often, so it's practical for you to know what they are all about. But we have many different programs for comparing the group means of groups, and that's what we are going to do during this lecture. The added value of a two-way or two or more way ANOVA compared with one-way ANOVA, where you could technically you could do several one-way ANOVAs and always introduce one fixed factor to explain what's going on with the dependent variable, difference between these groups, and then you have some other grouping fixed factor, to take that in. And naturally that is quite possible. The neat thing about the two-way ANOVA is simply that then you can also look at the interaction. So there might be something interesting going on where for instance, the experiment, the effect that you are looking for has something to do with some other grouping factor. So this kind of interaction is only made possible to see if you actually are able to put the two variables at the same time into the ANOVA. Okay. So here we would now have an ANOVA situation. This is just a thought experiment as of yet, but here we would have two independent variables explaining something, some dependent variable. So we would have, let's assume that we have some skill in some subject. Let's say some people are better in French than others. That would be a school subject, and there would be a test for how good you are in French. And then you would have a situation where you have people with some kind of learning difficulties, and so people, the other people, those who don't have this learning difficulty. And it would not be a great surprise to us if the people with the learning difficulties did not do as well as those without the learning difficulties. Okay, so this would already be something that you can test. You can put it into an ANOVA, Traditionally, we would, because you only have two groups comparing, the means of two groups would be something that you would use a t-test for. It's kind of before this course starts, but you can try it out. It works really nicely, and the only problem is that you can't have more than two groups. ANOVA gives exactly the same result as a t-test if you put in two groups, FX factor with two groups, like gender, for instance. Okay. Now let's assume that the teachers teaching French are trying out some new interesting teaching method. So here we have the normal situation before they start out something different, and here's what happens after. So slightly improved, maybe not significantly different results for the group with no learning difficulties. But here we see a big difference in the group with the learning difficulties. So you would see that on the average, maybe there is not a big improvement, but in the group of learning difficulties, in the group with learning difficulties, French acquisition has jumped forward. So this would be a very interesting and excellent result, indicated that you don't get worse results for those who don't have a learning difficulty, but you would have something that would greatly improve the learning and lives of those who otherwise would have serious difficulties in learning the language in question. Now this would be typically what we would call an interaction. So if the effect would be exactly the same in both groups, or there would be no effect of the teaching, the new teaching method, then there would be no interaction. But always when we get this kind of, the lines are not parallel, then any of these variations would be a typical indicator of interaction. So we use ANOVA to analyze the difference among group means in a sample. So again, the idea of being lazy here, we don't measure the population, because, for instance, if the population were all people who study French, that would take some doing. But we could take a sample of those, and that would make our life more easy. And then we are interested not only in the difference between the means of the different groups, but also the variation. And we can divide this variation of the results as between group variation and within group variation. And especially in ANOVA, we are interested in if the between group, if you compare these variances, if the between group variance is larger than that within group variance, then you have a situation where there actually is a significant difference between the groups. So here, for instance, you would have a situation, situation where the difference between the groups is rather small, may still be significant if they are large enough groups. But here you would have a situation where the difference between the groups is great. Again, typical situation with where the within group variation almost covers the between group variation, and the opposite here where you have a very large between group variation compared with the within group variation. And then you have different variations, different versions of these situations. You can have, in ANOVA, you can have more than 2 groups. So here we would typically have a situation with 3 groups, and the difference between group 1 and 2, they would have some difference in variance, but no difference in the mean. So no, the between group difference variation would not be significant at all. And then you have a rather extreme difference between the groups 1 and 2 and the group 3, the pink one here, and so on. You can have more than 1 group, and even just one group's difference from the others can cause a significant result in the ANOVA. Okay, as I said, you have some demands or some prerequisites before an ANOVA works nicely. So to have the means, you have to have a dependent variable, which it needs to be interval scale. You also, this here I sigh slightly. You also have the possibility of using ordinal scale variables, like a Likert scale variable. I totally agree, I totally disagree, or others of such nature. It is often done because people in education or human and similar sciences have a need to try to figure out if these are the items that we are using in a questionnaire, for instance, to figure out the structure, factor structure, how many latent variables are behind what people are saying. So that would be a situation that we could be easily interested in. If we only have individual variables, then you can't do an item analysis or factor analysis on them, and then you would have a situation where you would have a dependent variable that would be a Likert scale variable. But in these situations, you need to be careful, and if you want to do it really correctly, there are, as I said, non-parametric versions of ANOVA which are recommendable when you have this kind of ordinal scale situations. Also, the dependent variable should not only be interval scale, it should also be normally distributed. And we'll go into this later, but there are different ways of testing how well this normal distribution assumption is met. There are statistical tests for this. You can have a look at the histogram and see for yourself and so on, and different versions of approaching this are available in SPSS. It is also worthwhile noting that if you have a very large sample, then you have a special situation where if you think of your sample as a representation of the population, the larger your sample is, the closer it will be to the population. So if you have a small sample and it has some strange form or so on, then that strangeness needs to be big to be significant. But if you have a very large sample, then it will be already pretty close to what we expect the population distribution or population effect to be. And so even relatively small strange effects or differences are significant. So if you have a very large sample, small irregularities, for instance, in the normality are to be expected. You get significant results even if they are not important. Okay, also we need to have categorical variables as independent variables so that we have groups to compare. There's a third requirement, and that's that the variance of these groups should be equal, more or less. And there's a test called Levin's test, which tests for this between the groups if the variance of the groups are equal. And this should be non-significant, so I have probably written it the wrong way around here. The p should be larger than 0.05, simply because then you have a situation where the groups do not significantly differ in their variance. So significant would be smaller than 5% risk, and we would want to have a situation where the risk of accepting the hypothesis that the groups are equal is larger. So large risk of accepting the hypothesis that the groups are equal. In other words, saying it the other way around, small risk that they are unequal. All right, this is a totally fabricated situation. We have 4 groups, group 1, 2, 3, and 4, and a dependent variable. So a grouping variable, a dependent variable, this would be a typical one-way ANOVA situation. And you can't use directly a t-test because you have more groups than 2. All right, we were talking about the Levin's test. Here you can see already the result of this. So the Levin's test would give us a situation where the risk of accepting that the variances of the groups are different would be about 50%. So 50% risk, that's a big risk. So we wouldn't accept that idea. We would say that we can live with the idea that we can assume that the variances of the groups do not differ. Okay, so Levin works nicely. Next, we get the real ANOVA result. So here is there a difference between the means of the groups. And you remember we have 4 groups, and 20 cases. So then it counts the degrees of freedom here according to how large a sample you have. So if you have 20 here, 20 minus 1 is 19, and then you have 19 minus the 3 between groups and 16 within group variation. And then it simply gives us what it does here is this is this sum of squares divided by the degrees of freedom. Equally, this here is this sum of squares divided by degrees of freedom. And if you then count the proportion of this 49 through about 1, it's slightly more than 49, 50, 60. So that's where the F value, that's the test value which comes out, and that you don't have to count these during this course. It just helps if you know what the program is reporting. And here you can see already the test of the significance. So the difference between the groups would be highly significant with, again, 0.05 as a 5% risk, 0.01 as a 1% risk, 0.001 as a 1 promille risk, and here it is even smaller. So a very small group, very small risk that the groups would not differ. If you accept this result, then you can say that there is a significant difference between the group means. ANOVA gives us further results if we ask for them. We'll look first at the picture here, the figure, which is kind of neat. It is exactly the same story as in the table above, but below here you can see the important thing here is that place here in middle of the whiskers, that's the mean of the group, and you have the same 4 groups here, and then we interpret the whiskers and they are the same story as here. So these would be 95% confidence intervals for the mean. So considering that we have a sample, then the sample is always kind of a slightly distorted image of what the real situation is in the population. So if you have, it's kind of a mirror of the real situation. Better if it's a big mirror, less accurate if it's a small one. So the sample size is important there, but here you can see that you have, for each of these means, you have a lower bound and a higher bound confidence interval of 95%. So here you can say that if you look at the mean of a group and then you have its confidence intervals, you can say that within 95% accuracy you have, the population mean is also between these whiskers, so within the confidence interval, which means that you can already see here, if you have such a difference here, you can, and then you can say that in the population, these groups average mean would be somewhere between these whiskers and vice versa here. Then these two differences, not only are there is there a difference between the group means in the sample, but also in the population, we can assume that there's a significant difference between these groups. So in the same way, if we compare these, we can see that there's a great difference. Here there's a clearly smaller difference, but still, if you look at these whiskers and these whiskers, the mean of this group would not be within these whiskers and vice versa. So again, we would say that looking at this picture, that there's a significant difference between all the groups. All right, now think of this when you look at the table, and you will see that the result is actually exactly the same. You have here the means, so the first group mean, the second, and so on are, if you look at the second group mean, it's 9, and you see it's exactly 9 here. So we get the same result. You have the standard deviation, standard error. From these, the confidence intervals are estimated, and then you can see that, for instance, for the first group, the upper bound is 3 point something small, so it's very close to 3 here. So exactly the same story. And this, of course, would be one way of getting a better understanding of what's going on in the group. Not only that, but ANOVA also gives us a so-called post hoc testing possibility. And this looks complicated, but in the same way that we broke down the previous table, we can also get a grip on this one. So what's going on here? It's simply that you can see here the different groups. So you have group 1 compared with group 2, group 1 compared with group 3, and 1 with 4, then 2 with 1, which is same as previously, but the other way around, 2 with 3, 2 with 4, 3 with 4, and that's all this important stuff we have here. And we don't need to look at this so much as significant directly, and we can see that all of the differences are significant between groups. So this is actually what you would get if you had a t-test comparing each of the groups with each other. So group 1 with group 2, group 1 with group 3, group 1 with group 4 would be the t-test results are here. However, the post-tests are importantly slightly different from t-tests, because if you have just one comparison in your sample between two groups, then the t-test gives an accurate result of the significance of these, the difference between these two groups. But if you have, say, 100 groups, then you have a tremendous amount of different combinations, like group 1 with group 2, group 1 with group 3, group 1 with 99, and so on. So within that enormous amount of combinations of groups, there will be some differences between the means that are statistically significant even with a t-test, even though they are not real differences. So they would be kind of just because of random error, there will be such differences. About 5% of 100 comparisons would give such a result. And if you have 1,000 comparisons, then you would already have 50 such results, and so on. So it is important to have some buffer, so that you don't get overexcited with these comparisons and these comparisons, and Ponferroni and other post hoc tests provide such buffers. Also, this is of course a much quicker way of looking at it than doing all these separate t-tests separately. So we are happy that the machine does it for us on the program. Let's look some more at the normality of a distribution. You remember that we needed to have normal distributions for the ANOVA. And we are now looking at the dependent variable here. This is no longer just a theoretical example. This is actually a practical one. So we have the PISA general factor score of all the different tests within the PISA study on academic skills of the students together. And you can see that already if you, well, okay, let's break it down. First of all, within SPSS, you can go for frequencies, put in the variable you're interested in, and then you ask for a histogram. And you can ask for a histogram with the normal distribution drawn on top of it so that you can make the comparison. Here already we would say that it looks rather nicely normal, but there's a kind of a tooth gap here, and there's something sticking out here. So maybe it's not perfectly normal. And then we have to make a judgment call. Is this too skewed, too peaked, or something to be seen as a normal distribution or not? The next way of approaching this would be to use a descriptive statistics, so-called frequency distribution again, or so-called non-parametric tests. Descriptive statistics frequency distribution as in the previous, or the non-parametric tests. We'll get to the non-parametric tests soon, but here we look at the descriptive statistics, and there you can click on two interesting ways of looking at the normality of the distribution, the skewness indicator and the kurtosis indicator. And the skewness tells, you remember, how close to normality we are in the sense that if you have a large or small skewness, then you have a long tail either to the plus side and it's a positive skewness, or to the minus side and it's a negative skewness. So here we could already see that there's some skewness and it's negative. So tail is towards the small values of the scale. And then we can form an understanding of how big this is by comparing the statistic with the standard error of this statistic. So the standard error times 2 gives us a rough estimate of, is this a serious skew or not? So 0.032 times 2 would be 0.064. And 0.064 is smaller than the value of this. So of course it's negative, but if you leave out the sign plus or minus, then it's about 5 times bigger, this skewness statistic, than twice the standard error. So we would say that the skewness is significant, and that means that we should maybe be a little bit worried when we use this. Likewise, kurtosis can be again counted. So we have its standard error here, and then we see 2 times 0.064 would be 0.128, and that would be again slight, or this time it would be slightly bigger than the kurtosis, say roughly the same. So we would not consider this kurtosis too big. So typically you would have a big positive one or a negative one, or a normal would be close to 0. And here you would have a situation where it's slightly flatter than it should be, but on the other hand, that we wouldn't consider significant. So we would say that there's something a little bit fishy, a little bit skewed here in the distribution. And as I said, we have the third option, which is using a non-parametric test, a one sample non-parametric test called Kolmogorov-Smirnov. And here you can again see already, I mean, it's very simple. You just go to non-parametric tests, analysis non-parametric tests, and one sample, and then the Kolmogorov-Smirnov gives you already this box here with the significance. So there's a significant result, and that means that again we should be this also indicates that there's something slightly different from the normal distribution here, a significant difference. And it even tells us what to do, reject the null hypothesis, and the null hypothesis it has written here. So this is very practical advice, sound and practical advice. We tells us that there's something a little bit skewed in this. So we get the same result with all 3 different approaches. Now, if you click twice on the decision box there, you get this. So it also helps you to just have a look at the Kolmogorov's at the normality curve with the histogram. So we go different roads, get to the same result. And here you could quite easily see what we saw in the first picture. There is something a little bit strange, not perfectly normally distributed. This PISA general factor result. Okay. Now, you remember I told you that if you have just 2 groups, then the one-way analysis of variance will give exactly the same result as a t-test. Here, for lack of fantasy, I have used gender, difference between male and female students on the PISA general factor. So even though I already showed you that there are 3 different ways of looking at the normality distribution, and all of them show that there's something a little bit strange with this PISA general factor, we can have a look at what would the PISA result be for the male and the female group. And that's here. Now you can see that the difference, the boys' result is clearly not as good as the girls' result, and there's the whiskers indicate that the boys, the population mean of the boys is far from that of the girls. So clearly a significant result. And There are other ways of looking at this. So the significance you can see here again. The ANOVA tests the significance of the difference between the groups, the same result as we got here previously. But now we have also asked for a second variable here, or second indicator here, and that's the eta square. And that's an important indicator because people fall in love with statistically significant differences between groups. And even minute, really small, tiny differences, if you have a very large sample size, can be significant. And then it is of great importance that you not only test the statistical significance, but also the partial eta squared, which tells you how large is well, let's say, how large is the variance explained by this effect out of the 100% of the variance within of that variable. So here you have partial eta squared, and even though the significance of the difference between the group means is very high here, very strong significance. Sorry, I'm trying to find there. Then you can see that the partial eta squared is 0.02. It should be slightly more than 2% of the effect of the variance in the PISA results is explained by gender. So the previous picture shows us one result. It looks as if there's a great difference between the groups. But if you then look at the whole variance, then this great difference is only about 2%. So here we have the significant result. Here we have the effect size. And 2% is not that big. It means that 98% of the variance in the dependent variable is left unexplained. 98%. So when, for instance, Finnish ministers of education and the media often are very anxious that something very strange and dangerous is happening, and we are getting too big a difference between the groups, male and female groups of people in Finnish schools, then yes, it has slightly increased. The effect size has increased from something like 1.5% to about 2.1%. So it has increased. The direction is not really what we are striving for. But on the other hand, 2% is 2%. It's not the whole world. And maybe we don't need to change the whole educational system just because of a 2% difference. So this is what I'm talking about. This Shaw spoke about people being moved. Sometimes people are moved because they don't understand the result. Sometimes because the result that we show is actually something that we need to do something about. And in the latter case, I totally agree. We should be moved by this. But we should also we should have kind of a mental buffer. We should be able to be critical and not be moved by just any big numbers that somebody shows us. Okay, so how do we interpret these results? So now I have drawn the distribution of the girls and of the boys on the same mean general PISA data. And we hear so many different interpretations of this. The typical one in the media has been that the Finnish girls outperform the boys. And that is, strictly speaking, untrue. That's a lie. That's not what this data tells us. Now, the data tells us that there is, as you can see, a small difference between the means of the girls group and the boys group. That is true. That is what this tells us. And as we have seen previously, that difference is statistically significant, and there's a 2.1 effect size, percent effect size there. So it's a real difference, yes. But the girls don't outperform the boys, simply because if you look at the boys average, the blue line there, you can see that there are plenty of girls that are doing less well than the average boy, or vice versa. If you look at the girls red line average there, you can see that there are plenty of boys doing better than the girls average. So both ways clearly show us that all the girls do not outperform all the boys, and we should beware of saying things that are untrue. And also, if you have listened to some of our ministers of education, the great changes they are suggesting may also be overly strong reactions to very small effects. We know about clickbaits. We have seen them in international policy, and we know that people are moved by them to click and to act and to vote and so on. But even in statistics, a lie is still a lie. All right, how to go about this? Now we are doing it these previous were small scale examples. Now we are doing it big time. So again, as previously, you go to the analyze, and as I said, you have different versions of doing this. You can find one way and other ANOVAs from compare means, of course. But for practical purposes, we'll go directly here to general linear model. With the univariate version of ANOVA here, multivariate would simply mean that you have several dependent variables, but we won't do that during this course. There's a different version of that called the repeated measures ANOVA, which I would dearly love to see more often used, where you can see, for instance, a pre-test and the post-test results. So of the same student group before and after the experiment you have. So really cool stuff can be done using ANOVA. But here we have this the univariate version. You can select the variables just as, and this is again important to remember. You are proceeding in a very similar way to what you did in the item analysis, a very similar way to what you did in factor analysis. You again select the variables. This time you select one dependent variable. So here we have the general PISA score, and then we have the fixed factors here, student gender and highest educational parents. I should warn you that I have simplified this, so it's not, doesn't have 6 different categories, it has only 3. So primary, secondary, and tertiary education of parents. And again here, as always, the fixed factors are categorical. So gender is categorical. The 3 classes of education are also, you could say that they are ordered, but still we can treat them as categorical also. And we don't use a covariate here, but if we had some, sorry, again, oh, here. If we had a variable that we would want to control, that would be maybe confounding the result. So here, if we are really interested in the education of the parents, but not in their socioeconomic or economic situation, so we could control for the amount of money the parents earn per year, for instance, per capita, per year, and in this way we would see just the effect of the education without the combined effect of education improving your potential to earn more income, and your income also influencing the results of your kids. Maybe because you can pay for a better school, or maybe because the books and stuff that you have bought for your kids have the potential of buying for your kids also influence them. So in the case that you want to control some variable, then you can use it. You can put it here as a covariate if it's a continuous variable. Okay, how do we do the practical stuff that we saw in the pictures previously? Well, typically we want to have plots, because as you saw, at least for me, one good picture speaks more than 1,000 words. And very few people actually in their articles or their dissertations want to say 1,000 words where they can get away with one good picture and some explanation. Okay, so we have these 2 factors selected, gender and education of parents, highest education of parents. And what is going on here is that we can select, I typically put the categorical variable with more categories on the horizontal axis, and separate lines on the one with less categories. So gender has fewer than education of parents, so that's why I put it this way. You can try them out and do it the other way around. It's the same story, it's just in a different tapping. Anyway, when you then click on this add button here, it puts the plots here. So you can either have separate plots of educational of both of these factors, gender and education of parents, or you can have a combination of these. So you can see here where it has the HISCED kind of times gender. So it's a combination picture where you have both these things at the same time. And I have selected to click include error bars. here, and then we go ahead. From options, we can select, we were talking about the effect size previously, you remember the 2.1 of the gender effect. Well, here, when you go to options, you can choose directly the estimates of the effect size. We have the homogeneity tests, that was a Levin, to see if the groups have equal enough spreads, or if one is very sharp and one is flat in its distribution, and that kind of stuff. And that helps us see what's actually going on. And you can even change the significance level. So you remember that we have here tried out the 5% risk, but if you want to be really on the safe side, then you could change it, for instance, to a 99% risk. Sorry, a 1% risk, which would be here 99%. Sure of your interpretation. Okay. Also, you have a box here with post hoc testing. You remember the kind of t-test between each group in our data. And if you let's say it the other way around, if you have a small number of groups, the Bonferroni that we already saw is more powerful than the others. There's also Tukey's. There's actually two versions of Tukey here. You should actually have clicked the first one. I think here would be my suggestion. If you have a situation where you have a large number of pairs to compare, large number of groups to compare. Okay, and then we go ahead and start to, when we click OK, the ANOVA starts pouring out results. And here we have already the first table, and it just tells us what we have put in here. So we have put in about 30,000 Scandinavian students, and we can see that we have just about the same number of female and male. So it's a numerous n tells us that there are about 16,000 of female and male students in our sample. It tells us also that there's something fishy about the distribution going on here. So there are very few people with few adults or parents with highest education only on the primary level or less in the Scandinavian countries. Secondary education, vocational or upper secondary, there would be about 6 times more, and again many times more with university or polytechnical education. So that's just description, but now we get into the real stuff. This is already the ANOVA table coming out, and it has first a test of the whole model. So this is where we start. We look at this significance. If it's non-significant, then we actually don't need to go into the details to see the differences between the groups, because we can say that if this was not non-significant, then there's not anything real, any real differences to look at in more detail. Then number 2, we go into the direct effects. We have here gender and parental education. We see both of them being statistically significant. However, if we look more closely at the eta squared, we can see that the effects are not that big. So gender shrinks even more from 2% to about 1 promille, because the parental education actually takes care of a larger part of the variance. So that's about 3.5% of the variance of the PISA general factor is explained by parental education. Now, a lot has been said about the importance of the parental education and how much it explains and so on. All this is fine and dandy, but the real stuff is still importantly that even 4% is still not the whole story. So there's a lot of variance unexplained here. And if we really want to be excited here, we should see bigger effects maybe. Cohen in 88 gave us some kind of limits for where to get more or less excited. And he said that a small effect would be something of 0.01, so 1% size, effect size. Medium would be something like 6%, so larger than the one we have here for parental education. So we would say that both the gender effect and the parental education would have would be small in their effect size. And the large effect size would be something like 13-14% or more. Now then, I was also talking about the possibility of these having an interaction, and we saw the picture of what the typical interaction would look like. Here we can already say that the interaction, there is a slight interaction, but it's not statistically significant, and it explains just about nothing of the variance. So we don't have to get excited about the combination effect of gender and parental education. Here we can see first this large green effect here between those parents who, the kids of those parents who have a high education and the lowest education. So that's the biggest effect. And from this picture, of course, people would say that the effect of parental education is tremendous, but of course it's dependent on the scale here. So if we again remember that the scale here, now it's standardized. So 0 would be the average of the OECD country in the OECD countries, and 1 would be the standard deviation, and we would have here about half a standard deviation or a little bit more would be this. So it's not too small to be considered. It's something that we should look at. We should worry if it becomes bigger, and we should be happy if it becomes smaller, I think, in a system where we want everybody to succeed in education. But it's still not so big that we could say that it is kind of hindering everybody from the possibility of succeeding in education. Some people have to work a little bit harder. Another way of looking at it is that education is so important that it has an effect over generations. So well-educated parents have an added value for their children at least one generation, over one generation, as this suggests, but probably even more than one generation. So it's like a kind of biblical in that sense, that you have effects that don't just concern the kids in question, but also their parents. That's something maybe to become a little bit moved about. There's a clear effect of parent education. Educated parents have children who do better at school. You also see a small difference here between the girls and the boys. And that was also significant, but you can see that the size of this effect is much smaller than the size of the education, parent education effect. And you can even see a very clear a clear interaction here. Even if it was not significant, you can see that the difference here is bigger than down here. So there's an interaction between gender and parental education, so that the gender gap is larger with the highly educated parents, which is kind of strange. One would think that the highly educated parents would be able to support and buffer their children better. So kind of strange that this becomes bigger, but we don't have to go too far into the interpretations here, simply because this effect is not significant statistically in this sample. Okay, we can dive deeper into this and look at our post hoc tests. You remember the Tukey's and the Bonferroni's, and here we have Bonferroni because I'm only looking now at the differences between these three groups: primary education, secondary education, and tertiary education of the parents. And again, we can see primary to secondary, primary to tertiary, and secondary to tertiary education. And the other combinations are repetition. But anyway, all of these differences between the groups, as seen in the previous picture, are statistically significant. Okay, getting even deeper into trouble. No, looking at the Levin's test for equality of error variances, we already know what the result is. So Levin tells us that here we have a statistically significant difference between the groups. Well, we saw that the group with parents with primary level education is relatively small and probably not normally distributed either, and different from the group with the highest education, which is most common in the Scandinavian countries. So then you should preferably at least try out the results also using a non-parametric version of ANOVA. We have the Kruskal-Wallis, which does precisely this. So because of this statistical result here, we go to the Kruskal-Wallis. Here you see what the Kruskal-Wallis. So now you don't have. You go to, again, analysis, non-parametric tests, and then the independent sample Kruskal-Wallis. So instead of having one sample, seeing how normally distributed they are, now we have independent samples, which are in this case the different groups of children with different levels of educational background for their parents. And it gives us a significance. So here we directly have the result already, reject the null hypothesis. So a highly significant difference between the different groups. Let's take one step further. We double click the decision box here, and this opens up. So it gives us a box plot, and now we have the same result here as we saw here. So the primary education group has a lower level of performance on the PISA scores than the tertiary education group, and so on. And here we can see precisely that happening. So here we have the group with tertiary education, secondary education, and primary education background. And to understand this box plot, you need to know that because there was problems with the normality, it has now just shows that this is not the mean, it's the median. So half the group is on one side, half the group. So it treats it as ordinal scale, not as distance scale. Sorry. And you can see, if you look closely, that there is actually a difference, and it's a similar difference between the medians as we saw in the previous picture. And then it has the box contains half of the group. Sorry, trying to get here. So this box here is the, if you separate the whole sample into 4 equal sized lumps. So you have the lowest quarter, the second lowest, the third or second highest, and the highest quarter of the group. Here, that would be the highest quarter of the group within those whiskers. And you can compare these means, and you can see that they go nicely together with previous. And you can also maybe be a little bit more secure in your interpretations, because now you can see that you have this exactly the same result in 2 different forms. So you can do a non-parametric test to see if the differences seen in the ANOVA are the same as what you see here. The same. Usually they are, so it gives you a certain security in your interpretations. Now then, I have also picked some examples of how to present results and put them into our Moodle, but here this is a quite nice lectures on how to use APA style, or American Psychological Association, which is the recommendations we also follow for how to report different types of analyses. So here we would have one-way ANOVA, 12 participants in the high dosage group. Okay, this is not typically education, but you can take your own variables and use the same form. High dosage group had an average reaction time of 12.3 seconds, so that would be their mean, a standard deviation of 4.1. The 9 participants of the moderate dosage group had an average reaction time of 7 seconds with a standard deviation of 2.3, and 8 participants in the control group had a mean of 6.6. So now they talk about average and mean. I would talk about mean, mean, and mean all the way around. Through standard deviation of 3.1, and the effect of dosage therefore was significant. Well, I would first put the F value is 8.76 with the degrees of freedom here. So I would use this F value here with this significance would be then what I interpret. So I would not say therefore, I would say the effect of dosage was significant, and then I would just give this. But you can do it in different ways. The main thing is that you have a very simple, clear format to make your result understandable. And of course, it would be neat to have a table or a figure you could refer to here as well, so that people, if you have, I mean, this is a relatively simple one with just three means, or three groups with means easily comparable here. But even here, I would say that the difference here is larger than between these two. So maybe this difference is really significant, this is not. And the figure would help us in making these kind of interpretations. Okay, in a two-way ANOVA, it's slightly more complicated, but here we would again have two effects. So the diner's gender effect and it tells us that there's a significant effect for it, and then it starts explaining the average tip was significantly higher for men than for women, and it has a means and standard deviation of both groups. And then it has the other effect. So the first effect was the gender of the diner, men and women, and then it has the second effect, the effect of touching. So it's supposed to be that if, at least in some cultures, if the person who is asking for or who has been serving and who will get the money for the supper, if they touch the person who will pay, then it's supposed to be bring a positive effect, and they are testing it here. So what we see here is the main effect of touch was non-significant, so larger than 5% risk of being wrong. However, the interaction effect was significant. So again, while there is a difference between men and women, and there's not on the whole a difference between if you touch or don't touch the person who is going to pay, there is a difference which is important for people in the restaurant business. If you touch a woman, you don't get extra tip, but if you touch a man, you do, which is interesting. Now, I recommend that you find examples of your own that are more clearly connected with educational sciences, but these already tell us that there is a story, and that story needs to be said in a short and comprehensive way, so that people reading it can understand what is going on, and so that they can be convinced by the results. Thank you very much for this lecture. See you next time. Bye-bye.